Um, Hello, everyone. My name is Germán Rivera. I'm originally from Colombia, but live in the US right now. And it's an honor for me to be here in the Ada Developers Workshop. I'm going to talk about the HiRTOS project, Multicore RTOS, written in Ada um, or in the Spark subset of Ada. And so this is what I would like to cover. First, give kind of a design overview of this HiRTOS, and then describe the internal design of the thread scheduler. And if we have time, then I'll talk about the separation kernel. If not, then I'll skip that, but it will be in the slides if you guys are interested. And then I'll talk about how to port HiRTOS to other platforms and some future work ideas that I plan to work on myself, or that if anyone is interested, um, feel free to also explore those ideas. So HiRTOS is a small real-time operating system and separation kernel written in Ada, and is targeted for small microcontrollers and embedded platforms that at the bare minimum have an MPU, a memory protection unit, but is not. It doesn't require like more advanced hardware like an MMU or something like that. So just a memory protection unit. And HiRTOS is available for download as an alias crate, and there is a separate alias crate for the separation kernel, and the code is available in GitHub. The original intent was to design a very simple RTOS that supports multi-core. And for the sake of simplicity, the current design is such that each CPU core has its own instance of HiRTOS, and there is no communication between cores, so there is no resource sharing between cores. So every core runs its own copy of HiRTOS state. So mutexes and condition variables are the only synchronization primitives. So interestingly enough, most RTOSes in mainstream have semaphores, event queues, or message queues, event flags, and but HiRTOS doesn't need that. Although if someone wants to implement them for HiRTOS, they can be easily implemented on top of just mutexes and condition variables. But also for the sake of keeping the RTOS small and the simplicity of the design, it was kind of just better to keep mutexes and condition variables as the only synchronization primitives. Mutexes support two forms of preventing unbounded priority inversion. One is priority inheritance, and the other one is priority ceiling. And when you create a mutex, you decide which type of protocol you want. Condition variables can be waited on with interrupts disabled, and that makes it possible to be signaled from interrupt handlers. Otherwise, if you signal a condition variable from an interrupt handler and a waking thread doesn't have interrupts disabled, then the signal of the condition variable may get lost. And that is also necessary in order to avoid having semaphores. Another unique concept is the concept of atomic levels that can be used to disable the thread scheduler or interrupts at a given priority or completely. Threads are bound to the CPU where they are created, and they cannot migrate CPUs. That is also for simplicity and predictability for real time. All RTOS objects such as threads, mutexes, and condition variables and timers are allocated statically, and no dynamic memory allocation is supported or used in HiRTOS. That is also for predictability and determinism, and for safety. So no bugs of using the allocated objects are possible because the allocation is not permitted. Once you create a thread or a mutex or a condition variable, there is no way to delete it or deallocate it. All application threads run in a privileged mode, and the only memory that they can access is their own stack. If they want to access global memory or MMIO space, they have to make a system call to ask permission to HiRTOS, or they can elevate the privilege to run in privilege mode. So another interesting feature of how HiRTOS was designed is to use pointerless data structures, in alignment with what Jeffrey presented earlier. Yeah, I also think that access types should be avoided if possible. So in this case, the way since the RTOS is kind of very close to the metal and is using a very minimal Ada Runtime library, no advanced Ada features can be used unless you make the runtime library bigger. So not object-oriented constructs of Ada are used. So in this case, to avoid the use of pointers, we just use indices of into arrays of objects, and that is our way to kind of make the connection between objects. For example, a thread that is associated to its built-in condition variable or its built-in timer, it has an index to refer to the corresponding object of that type. Also, the other important consideration to avoid pointers in this case is how to implement linked lists without using pointers. And then for that, we have a generic linked list module based on, indices into arrays of nodes. And in that way, we don't have to use pointers. And it's a generic Ada package that is reused 3 times, one for the thread queue, one for the list of mutexes owned by a thread, and the last one is for timers. So this is just to give you an idea. This is how the kind of the code of the generic linked list looks like. And now, so where HiRTOS runs currently? So it runs in on Cortex-R52 cores. That is a multi-core processor. There is an ARM fixed virtual platform FVP simulator available for free. So that is the platform that I used to originally develop HiRTOS. So the screenshot there shows an example of 4 cores. So each core is printing to its own UART, and so you have threads running on each core, and they run like independently. So yeah, threads of different priorities running on each core. HiRTOS also runs on another simulator called Renode. Renode is a very interesting simulator, kind of equivalent to QEMU, that allows you to create your own, SoC platform, adding simulation for various kinds of peripherals that are custom to a given SoC, whereas the ARM FVP simulator is fixed. That's why it's free. But the Renode simulator is open source, and so it can also be used for free. And they happen to have a simple model for the Cortex-R52 with 2 cores, but it's kind of the same code, the same binary that runs on the ARM FVP, the same binary of HiRTOS that runs on ARM FVP also runs on this platform. So this is kind of the same example. And then finally, so far the initial port only supported Cortex-R52, right? So then I said, oh, it would be nice to support RISC-V. So what is the cheapest platform that I can get RISC-V 32-bit platform on? So the cheapest platform turns out to be the ESP32 platform. So this is the older one, that is the ESP32C3. There is a newer one that is called ESP32C6 that HiRTOS has not been ported to that yet. But so this was kind of to prove, let me kind of enhance the portability of the code, because you never know how portable is your code until you port it to a new platform, and then you realize, oh, this needed some refactoring because it was not done properly the first time. So like just to do a reliability test, I have at home continuously running one of these little ESP32 platforms, and this screenshot was like a few weeks ago that shows that it has been running for 1,000 hours. Right now it's probably 1,200 hours with no crashes, which is kind of not kind of is kind of an achievement in itself, because if you have concurrent software running continuously for a long time, you can have race conditions always. So this is running a simple test of threads, a thread mix of different priorities, and so it has been working solidly. So now let me switch gears to talk about the code architecture of HiRTOS. So the original motivation was to have a replacement for FreeRTOS that is safer, so written in Ada, and and I say architecture vision because this has not been implemented yet, but the idea is to have some shim layers on top of the HiRTOS API to allow C or C++ applications to call HiRTOS. Indeed, the idea would be to provide a shim layer for FreeRTOS, so that, like I call those skins, so that HiRTOS could have a skin to pretend that it is FreeRTOS, so that you can have a FreeRTOS application that could be linked with HiRTOS and without having to change the application. Or most likely, another layer that could be added is to run on top of CMSIS. That is a kind of a standard RTOS API that is kind of RTOS independent. There are multiple RTOSes today that support that API, like FreeRTOS. There is a CMSIS RTOS layer on top of FreeRTOS, on top of Zephyr, and maybe other RTOSes. So then that would be another way to expand the use base of HiRTOS. And then so that layer sits on top of HiRTOS proper, and HiRTOS proper is split in two layers. The HiRTOS platform independent functionality, and then a porting layer that kind of isolates the platform dependent parts of HiRTOS, and that both of those sit on top of a minimal RTS that is kind of using the GNAT compiler terminology for baremetal Ada runtimes. You can have like full like zero footprint, small footprint, large footprint, and all that, right? And in the case of the small footprint, you have tasking. In the case of the zero footprint, you don't have tasking, but at least you have a dependency on a startup code, a reset handler. And so what I decided is go sub-zero, if you will. Below zero means not even startup code, so just the bare minimum components of the runtime library. I borrowed them from the GNAT library for the host. And then I said, well, just the bare minimum Ada packages for the Ada runtime to write bare metal software. Of course, then you have to provide the things that now you don't have, like your own reset handler, your own UART driver to print to the UART, your own timer driver, and so on and so forth. And then this is if you want to use HiRTOS exclusively from Ada, which is easier. Currently, you have the interface to call into HiRTOS, but ideally we should have another skin of FreeRTOS that presents itself as the Ada tasking runtime, so that Ada applications that use the tasking primitives of Ada could run unchanged, but that has not been implemented yet. But so that is kind of the last part of the architecture vision that I have for that. Now, the internal layering of the code is presented in this slide. So the top layer is the APIs. So you have like the general APIs of HiRTOS. Then you have APIs that are, so basically HiRTOS could be seen like the ham in a sandwich, right? The top bread are the applications that call into the APIs to create threads, mutexes, condition variables, and use all those RTOS resources, right? And then the bottom bread is the part that interfaces with the platform-dependent code and with the hardware. So that layer, so you have like things that are for interrupt handling, things that are for memory protection, and so on and so forth. And then the internal modules for the RTOS objects, like threads, mutexes, condition variables, and so on. And then you have the internal layers that are I have, I call them underscore privates, that are supposed to only be used by HiRTOS code. And then below that, you have the porting layer. And the porting layer, then you have the various kind of components that are necessary to port HiRTOS to a new platform. So you have architecture-dependent parts on the left side, and on the right side. So architecture-dependent parts are just CPU architecture-dependent code, and then on the right side are things that are CPU architecture independent, but are hardware dependent for the given board or platform or SoC or microcontroller that are beyond the CPU architecture specifically. So then you have like typically an interface for handling interrupts and a low-level debug interface that is just for now providing UART output so that you can debug using the UART. But in platforms that have self-hosted debug features support, like the Cortex-R52 and the RISC-V of the ESP32, my plan is to add a GDB, a built-in or self-hosted GDB server, so that you can do debugging with GDB without having to use JTAG or any hardware interface. But that has not been implemented yet. Okay, so now the thread scheduler. So one of the most interesting pieces of an RTOS is the thread scheduler and how the context switch logic is kind of designed and implemented. And I thought of writing this HiRTOS as a kind of as a vehicle to teach how to write your own RTOS, and just to demystify that, writing your own RTOS is not that hard, and especially if you use an elegant language like Ada. So that's why kind of I documented this kind of at the level of detail that can be easily understood by anyone interested in maybe taking a look at this and decide to write their own RTOS. Okay, so the thread scheduler. So the first part is when you have a bare metal program, you have main, and then you create a bunch of threads or tasks, and then you call an API to start the scheduler to switch on tasking. That is typically what you do, right? So in this case, then this is what this first part shows, is that you create a bunch of application threads, and then or well, before doing that, you call the API to initialize HiRTOS, and then you create one or more application threads, and then you start the scheduler, right? So when you start the scheduler, then that starts the timer to start generating the tick for the RTOS, and then you perform the first context switch. Then the first context switch is implemented such that is like HiRTOS pretends that is returning from an interrupt to the first task. And that is because up to that point, HiRTOS had been running in the reset handler, which is interrupt context. So then the context switch for the very first task is implemented by just pretending that we are returning from an interrupt. So we call an API that is called interrupt handler epilogue, and that calls into the bottom of the bread, calls into the ham that is HiRTOS, and that calls an API that is called exit interrupt context, and that will provide return the stack for the highest priority thread, and then that is how the first thread starts. Okay, so now the tasking has started, right? So now there are two types of context switch that can happen: asynchronous context switch and synchronous context switch. And that is like how the scheduling entry, the entry points of the scheduler are designed with asynchronous and synchronous ways. So what are the asynchronous ways of doing thread context switches in HiRTOS? And I think this is kind of in general how it's done in any mainstream RTOS. So this is the asynchronous context switch is necessary to have thread preemption, right? So basically what happens is that every time that an interrupt fires, typically the timer interrupt, but also any other interrupt, that HiRTOS intercepts the interrupt, and then on entry to the interrupt, it saves the context of the running thread, and then calls the interrupt handler, and then on exit, it calls the part that runs the scheduler to select the thread that the next thread to run, and then switches in the context of that thread. So that is kind of shown here in this sequence diagram, that basically an interrupt fires on entry. You save the interrupt the context of the thread that was running, let the interrupt handler run, and then on the exit path from handling the interrupt, you call the thread scheduler, which will select the next highest priority thread to run, and then that returns the stack pointer for the new thread, and then you do context switch to the new thread. So yeah, this is done here. And then synchronous context switch. So the synchronous context switch, that is the second form of entering into or activating the thread scheduler, is when you call RTOS primitives that can block the running thread. Like when you call into wait on a condition variable, or even when you signal a condition variable, you have to call the scheduler because you may be waking up a thread that has higher priority than the current thread. So then that is, so all these primitives listed here are entry points into the scheduler. And then, yeah, I have sequence diagrams here for that. And sorry that I think I'm running out of time, so I'm gonna skip this, and I'm gonna well, just to give you an overview of the separation kernel. The separation kernel is basically a variation of HiRTOS, in which instead of scheduling threads, we schedule partitions. And a partition is nothing more than a thread plus a slice of memory and a slice of MMIO space. So then this is to have isolation between multiple contexts, because in simpler HiRTOS, you don't have memory isolation between threads, right? It's still safe because the threads have to ask permission to a HiRTOS to access global memory, but it still is not taking advantage of the hypervisor mode of the hardware. So if you have a hypervisor mode in the hardware, like Cortex-R52, then you can be a little safer by having partitions. That means chunks of memory that are completely isolated from each other, and then you can run an RTOS within each partition. And then a test case that I have for that is shown here. Also in the ARM MVP simulator and in the Renode simulator, what you see here in each of these windows is the UR output of the separation kernel running on each core of a 4-core processor. And on each core, what we are running is 2 partitions, and each partition is running HiRTOS. So HiRTOS is running within HiRTOS in a way, because the separation kernel is scheduling now, instead of threads, is scheduling partitions, and then each partition is running its own HiRTOS. So there are 2 partitions, each partition running 8 threads, and they, there is context switch there, and that is kind of how that works. This is the same thing, but with 2 cores, but running on the Renode simulator. Now, to finish, then what is necessary to port HiRTOS to a new platform? So you have to implement the CPU architecture dependent part first, and then you have to implement the platform-specific interfaces for the new SoC or board or simulator, right? So then the CPU architecture-specific parts are the startup code, the interrupt handling prologue and epilogue, the interrupt controller driver, the CPU architecture-specific timer driver if available, like the Cortex-R52 has one, and then the memory protection unit. And then things that are beyond the CPU architecture are like the UART driver, the external timer in case of the platform doesn't have an internal timer, like the ESP32, for example, and then platform-specific hardware initialization. Interestingly enough, in the ESP32 case, I got away by not having to implement platform-specific initialization, because I let ROM, I just leveraged what ROM did before. ROM, the bootload, the stage 0 bootloader in ROM loads HiRTOS as the stage 1 bootloader, and then so HiRTOS just runs on whatever the ROM already initialized, and that's so future work. There are this is the laundry list of things that I think can be done. One interesting idea I have to make HiRTOS safer is to, instead of having the idle thread, like just not doing anything, use those spare CPU cycles to run what I call a safety patrol thread that will check safety properties of the system. And so that is an example to make things safer. And then, yeah, these other things, and I think, sorry, I think I'm running out of time. So yeah, basically this is, yeah, that was the last slide. So thank you very much for your time.
Thank you. Do we have any questions here in the room? There seem to be none. Do we have questions online? Oh, yeah.
No questions so far.
Okay, then since we are basically on time, thank you for speeding up the presentation a little bit. Sorry for the time constraints. But then I would have a very simple question, and that is, what kind of level of proof do you have within Spark?
Oh, yeah, that is a very good question, and that is one of the to-dos in the future work. Is I hadn't done formal verification with GNAT probe yet, so I started kind of running on recently GNAT probe. I had a problem that it was GNAT probe was crashing on something that it was using the address attribute in a precondition. So I figured out that if I disabled that, I could run all the way. So I'm at that point that I'm able to run GNAT, the open source version of GNAT Probe without crashing, but I haven't done formal verification yet. So that is kind of the next step, one kind of expected next step, given that the code is written in Spark.
Nice. Thank you.
Thank you.